We just watched a video from Lethal Weapon where Mel Gibson was shot and was propelled backwards into a plate glass window. We established that that wouldn't really happen because in the end, if Mel Gibson received enough momentum to be propelled backwards, then he must have gotten it from the pellets from the shotgun. Well, then that means the guy shooting the shotgun must have received the same amount of momentum. Well, he wasn't propelled backwards. So if the guy shooting it isn't propelled backwards, then the guy that gets shot also isn't going to be propelled backwards. In the end, they should have the same momentum. We established that as part of the law of conservation of momentum. The law of conservation of energy, you remember from Physics 20, says energy can't be created or destroyed. The law of conservation of mass in chemistry says mass can't be created or destroyed. The law of conservation of momentum says momentum can't be created or destroyed. In other words, the total amount of momentum will remain constant. It won't increase. It won't decrease. It's conserved if we have an isolated system. Now, what's an isolated system? This is grade 10, science 10 here now. What's an isolated system versus a closed system or versus an open system? Yep. Good, good. No matter or energy in or out. That's the important thing here. No matter or energy in or out. If we're looking at a collision and all of a sudden there's mass entering the system, then the total amount of momentum will remain the same, but we have to account for all the mass. In other words, we have to make it an isolated system. In other words, we have to make the system big enough that there's not really any mass entering the system. We're accounting for that mass both before and after the collision. Same thing with energy. If there's friction in this, well, then really what happens is friction takes away energy from the system. That means that momentum is also lost. Where does the momentum go? Well, it goes to the earth. If we were looking at friction, we'd have to account for the movement of the earth as a result of friction as well. That's difficult to do. It's possible, but it's difficult to do. What we have to do is make sure that we include everything. If we include everything in the system, all the energies, all the masses, no energy or mass in or out, make the system big enough that we're not having any energy or mass in or out, then we can say that momentum is conserved. Now, it's difficult, let's say, to consider the mass of the Earth in a system, the movement of the Earth. So what we typically do, so that we don't have to worry about friction or air resistance or some kind of wind or some kind of other force or some kind of mass going in or out, what we typically do is look at immediately before the collision takes place, immediately after the collision takes place, so that no other forces really have a chance to do too much. Then we've got what amounts to pretty much an isolated system. Okay, let me write down a quick little definition of this. An isolated system, no matter or energy in or out. What does that really mean? In the end, how do we think of this? If you have no matter or energy in or out, basically what it means is that we have no external forces. If you don't have friction, then you don't have any energy in or out. If you don't have wind, then you don't have any energy in or out. So as long as you have no external forces, we can use the law of conservation of momentum to solve the problem. Now, we get a bit of a problem here, though. For 4 days, we've been working on impulse. We did an activity. We did qualitative impulse, we did impulse graphs, and we did numerical problems involving impulse. All 4 of those days, we defined impulse as the change in momentum. Now we're saying momentum can't change. We wasted 4 days talking about a change in momentum when momentum can't change. Momentum can change. If we look at the individual objects within the system, they gain or lose momentum. If we look at the system as a whole, then the momentum stays the same. Let's go back to that gunfire again, gun firing. Fire the gun. What's the momentum of the gun and bullet before you fire it? 0. What's the momentum after you fire it? What's the total momentum after you fire it? 0. The total momentum of the entire system remained the same. But what was the momentum of the bullet by itself before the gun was fired? 0. What's the momentum of the bullet after it was fired? Something, right? If we look at individual objects within the system, then momentum changes. There's an impulse. If we look at the momentum of the system, the momentum will stay the same. Because as the bullet gains momentum, the gun must lose momentum or have negative momentum in the opposite direction. We're going to use this to analyze collisions and what I call explosions. Fire a gun, that's like an explosion. Okay, a bomb goes off, one object. The bomb becomes several objects. Fire a gun, one object. The bullet and the gun combined become 2 objects, the gun and the bullet. You take one of those big, heavy medicine balls. Sometimes they have in training, when you're cross-training. Throw it. It goes forward, you go backwards. One object became 2 objects. It's an explosion. Whenever you have an explosion or a collision, momentum is conserved. And remember that we can still analyze these problems using impulse, but if we do that, we have to look at an individual object. If we want to use conservation of momentum, which is what we just learned, we have to analyze the system. So we want an equation, right? Whenever we're talking about solving problems, we always want an equation. But the equation here is one that's not on your data sheet. Because it's not really an equation, it's more of a law than an equation. Pi equals Pf. What does that mean? Well, it means the initial momentum equals the final momentum. If momentum stays the same in an isolated system, then initial will equal final. We don't have to have that written down on our data sheet. We just have to remember what the law of conservation of momentum says. Now, that's not going to help us solve anything the way that it's written now. We have to sub in some expressions to help us solve for something. We're going to say Pi, initial momentum, would be M1 V1 initial plus M2 V2 initial plus, well, depends on how many objects you have. If there's 2 objects before the collision takes place, 2 cars collide with each other, then we're going to say M1 V1I plus M2 V2I. If there's 13 cars colliding with each other, then we'd say M1 V1I plus M2 V2I plus M13 V13I. You have to have an MV term in for every object that you have before the collision. But you also have to have an MV in for every object that you have after the collision. If 2 objects hit each other and bounce apart, then we're going to say the final momentum is M1 V1F plus M2 V2F. If there's 13 objects, then you're going to add another 11 terms in there. An MV for every object after the collision takes place. Let's do an example. 9.6, page 477. We give you, here, I'm going to cross this stuff out because really we don't want to see this. This is just the givens, right? Here's the scenario. You got a wooden block attached to a glider that has a combined mass of 0.2 kilograms. So this block / glider, 0.2 kilograms. They're at rest on a frictionless air track. An air track, by the way, don't see air tracks a lot anymore. We had one when I was in high school. But what an air track is essentially is this tube that has holes in it. You pump air through an air compressor into this tube. Air goes out the holes and then allows a cart or a glider to ride on that cushion of air. It allows you to do pretty much frictionless experiments. What they're doing here is firing a dart gun at this block of wood that's on this glider. And then they want to analyze the collision between the dart and the block of wood to determine what the velocity of the dart was just before the collision took place. We did this experiment when I was in high school, except we didn't do it with an arrow, a bow and arrow. We did it with a pellet gun. I remember one day the teacher said, hey, does anybody have a pellet gun? And one kid puts up his hand and says, I do. Teacher says, can you bring it tomorrow? This is back in the 1980s when it was okay to bring guns to school. So I remember the next morning, he's walking down the hallway with a rifle over his shoulder. And nobody said anything because if he had a rifle on his shoulder in his school, there must be a good reason for it. So he walks down to the physics classroom, leaves it there for the day, and then we go to do the experiment in class. The way this works, by the way you actually record data with this is by an electric spark. It sparks 60 times per second and then records, makes a little dot on a piece of paper 60 times per second. You could record the motion that way. So this kid, I remember very clearly, there's plasticine on this block. He fires the pellet into the plasticine, but he wants to get really, really close to it, right? Because he doesn't want to miss. So the teacher says, get a little bit closer, closer. So he gets really close, like within an inch or two of this block, gets ready to fire, and then all of a sudden the current jumps from the spark timer to the barrel of his gun. So he's literally being electrocuted as he's holding onto this loaded gun, as everybody else in the class is laughing hysterically at him. Which in hindsight, maybe that shouldn't have been our reaction. A guy shaking uncontrollably with a loaded gun in a school. But everything worked out. It all worked out. We were able to do the experiment in the end and calculate the velocity of this pellet. I don't remember what it was, but we were able to calculate it. Okay, how are we going to do this? Well, it's a conservation of momentum problem because it's a collision, right? We've got a collision between the arrow and the block. We're going to call the block / glider M1. We're going to call the dart M2. Two masses, right? You got the dart, you got the block. This is a velocity. This is going to be VF, not V1F, not V2F, because they're together now. The block and the arrow are one object. They stuck together after the arrow hit the block. So we're going to call it VF. We're looking for V2 initial, V2I. The speed of the velocity of the dart. Hold on one second. The velocity of the dart before the collision took place. Anybody know what V1I is? What's V1I? Quick. 0. Good. Okay, let's finish this off. Don't pack up yet. Okay, and we'll be done in just about a minute and a half. Okay. Pi is equal to PF. There are two objects before this collision, so let's put in two terms. M1 V1I plus M2 V2I. There is one object after the collision takes place, so we're going to just say MV. One object because the dart stuck to the block, so it becomes one with the block. Why did I do that? Yeah. Right. Doesn't matter what M1 is. M1 times 0 is 0. So just cross that off. Save yourself the bother of writing that in. M2 is 0.012 kilograms times V2I, which is what we're looking for here. What's M over here? What's M over here? The quicker you tell me, the quicker we get out. Matt? Yeah, it's the combined one, right? 0.212 kilograms, and the final velocity here is 0.78. Now, before you calculate this, I want you to take an educated guess. Do you think V2I is going to be bigger or smaller than 0.78? What do you say? Should be bigger, right? Why? Good. Same momentum, much smaller mass. It's going to have a much larger velocity. Okay, so what we're going to do here now is multiply these two numbers together, divide it by 0.012. Anybody have the answer for that? Thank you, Josh. 13.8 meters per second. So you're right, Matt. It is bigger because it's lighter. Your homework tonight, guys. Practice problems on page 477. That's it. Just two questions. Okay. Does that make sense? All right, let's get those two questions done. And I don't know if I mentioned this to you before or not. We're going to have a quiz tomorrow on, not on this stuff, Quiz tomorrow on impulse. Quiz tomorrow on impulse. Okay.